Swayam Prabha. Digital India. Educated India.
Today we would be talking about improvement of bearing capacity using geosynthetics. The problem of bearing capacity is something that is very important in geotechnical engineering. When the applied loads are more than the existing resistances, we always know that the factor of safety is less than 1. But in some cases, for example, you would like to improve the bearing capacity. So, you would like to increase the factor of safety then by, say, for example, in a present case it could be 1.3, you would like to make it to 3, something like that. So, when you want to increase the bearing capacity or reduce the settlements, you need to have some sort of improvement in bearing capacity. We have seen in the earlier classes that one can use the bearing capacity improvement techniques such as stone columns, then prefabricated vertical drains. Many techniques are possible, even additives are also there. So, we have seen that these are all very useful techniques to increase the bearing capacity. In this class of improvement techniques, reinforced soil technique is something that is very elegant because it has the principles are somewhat simple and well understood, and it appeals to many people because it is more of mechanics oriented, and lot of work has been in the recent times in this area, particularly because you have so many companies producing geosynthetics. So, this technique has been used very effectively in the improvement of bearing capacity of foundation soils. Many people have studied this work. In fact, even if you can just see the latest papers also in this area in the ground improvement journal, there are, I just mentioned that you have a number of journals in this area. One is the ground improvement journal, you have from ground engineering journals, you have there are many journals, Geosynthetics International, Geotextiles and Geomembranes, you have many journals in this area. They have many types of studies, experimental studies, numerical studies, analytical studies, field studies, there are so many. They were clearly able to bring out the advantages and possibilities of the improvement of bearing capacity and stiffness in terms of the load displacement behavior or load settlement behavior, because we try to do a plate load test. A simple case is that you try to do a plate load test on a typical soil and then put the reinforcement and again do a plate load test, how it can improve. So, in this section or in this class today we would be talking about bearing capacity improvement in the case of sands. As I just mentioned, lot of work has been done in this area, lot of work both in terms of the experimental work and analytical work, even you can think of numerical work and also think the field studies. And what people try to say is that, how do you say that there is an improvement? We try to have a factor called bearing capacity ratio, okay, bearing capacity ratio, which is called BCR, which is nothing but the bearing capacity improved to what was existing earlier. Say for example, if there is only a 5 ton per meter square earlier, you would like to make it to 20 by 4 would be the bearing capacity ratio. This is what we look for. A typical example could be that say for example, this is the bearing capacity of a unreinforced soil, right. So, this is unreinforced soil, this is a geonet, this is the different types of geosynthetic materials. You can clearly see that this load displacement curve is considerably altered because of this. You can see that at the same settlement, like say footing settlement, say for example, you are taking about 2%, 4%, you can say that the load here is maybe 150 here or 140 here, but then when you just put some sort of reinforcement, it went to as high as 250. This is in a simple plate load test like this, where you apply some load and you have a foundation size, say for example in a laboratory scale. Actually this is a laboratory result. In fact in our institute also we have done lot of work. This is a typical result. In fact we also published number of papers on these lines from Institute of Science, where we can clearly show that bearing capacity improvement is possible by using some sort of reinforcement like this. Say for example, you can see clearly even the settlements also, because the moment you say that there is an improvement in bearing capacity like this, even there is a reduction in the settlements. So, like say for example, if you just go at this level 150, you can definitely see that at that 150 bearing pressure there is a settlements a little higher, but whereas in this case it is lower. So, one can make it even very stiff, like it can be like this. Okay. Then the obvious question is, how do you do this design? The thing is that we know that by putting some sort of reinforcement, like you have seen in the previous slide, that one can improve the bearing capacity. But then how do you calculate is something that we should know, and in fact Binkwith and Lee in 1975, actually it is a paper of master's thesis of the Binkwith and Lee was a guide. They prepared this paper, which has lot of experimental work, lot of analytical work also. In fact that is the first study, and it has been quite useful. Of course there have been many studies in this area, even last year also we had some analytical work done in these lines. The fact is that it has been effective, and there should be simple methods of calculating this method. We will see how it can be done. And one way is that, okay, we know that when you put some sort of reinforcement, it has to be effective. If it is not effective, you should know why it is not effective. So, we say that we should be able to understand why why it can be effective, or there could be some conditions under which it cannot be effective. So, to develop this design procedure, we should take care of the mechanisms by which it may fail. Say for example, a particular thing may fail in a particular direction. So, you see that you try to handle that particular direction, see that the failure does not occur. So, these researchers have identified certain mechanisms that we will see. There are three types of mechanisms that they said could be possible in the case of reinforced soil. Even reinforced soil may be there, you may put a nice reinforcement here, but if the depth, say for example the depth of the reinforcement is say this is a breadth of the footing, like footing is here, and you have to see that this reinforcement is somewhat close to this, we have to see that the failure lines, that the failure surfaces that we have are intersected, otherwise there is no use. Like if there is a lot of distance between this bottom of the foundation and the top of the reinforcing element here, then there is no use. So, you would like to avoid this possibility that the shear above the reinforcement will not occur. So, that is like d by b should be more than 2/3, like it should be quite close, like okay. So, it is normally we will see that some guidelines also that if d by b is more than 2/3, the shear failure occurs. So, the obvious thing is you should see that it should not be more than 2/3, it should be say for example 0.5, it could be 0.3. If you see that the reinforcement is somewhat close to that, then it is possible, right. This is one important thing. So, this we call it shear above the failure shear above the reinforcement is a failure mechanism. Second thing is that you provide, say d by b is okay, less than 2/3, the condition is satisfied, but the number of ties, tie is a tension member, the tie is not much, like you put one reinforcement or two reinforcements, then the possibility is that short ties and the length is not sufficient. Okay. If the length is not sufficient, what is going to happen? As I said, the principle of reinforced soil is that you have to have tension also mobilized, and also the pull out resistance. If the length is not adequate, so it may not really develop frictional resistance completely, and even if the friction is developed, it should be able to sustain that friction by pull out resistance. So, that is the reason I said the factor of safety, there is always a relationship between the pull out resistance and also the tensile force developed. Okay. So, if the short tie occurs, then short ties, there is a slip. So, this is what we just try to show in the form of a slip. So, short ties are tie pull out reinforcement, tie pull out we call it. Okay. Then there is another possibility, like it is like tension failure, like if the reinforcing element itself is not strong enough, definitely it can break, right. D by B is fine, but the length is also fine, but they all are very inferior elements. So, then there is no use, right. So, and all these, so we should see that the design should be such that all these three mechanisms are satisfied. If somebody can come out with another mechanism, nice, like that, you can always think of these mechanisms and see that they are all avoided. Okay. They are all simple assumptions, and what he did, analytical work, how did he do that? Like this is a B foundation of the, this is a foundation, B is a foundation width and depth of the foundation is df. Okay. So, what we assume is that beneath the foundation there are 3 zones, essentially 2 zones, zone 1 and zone 2, and of course, zone 3 is not here. So, zone 1 and zone 2. Okay. What it means is that you have a foundation system here, and then actually you have a reinforcements like this, that is what we are trying to, actually imagine that you are trying to place some reinforcements at some depth, and what happens, you take the center line of the footing, and based on the elastic stress distribution, as I said, reinforcement causes shear, shear is important in reinforced soil, right. So, what we calculate is that we calculate the distribution of shear strain and shear force, actually shear stress here, shear stress distribution is calculated, like when there is a load applied, it is minimum here because of the 0 here because of the symmetry, and it just goes like this. Okay. This one can get from Busnesque equation. We know that in undergrad courses we studied how do you calculate normal stress if a load is applied here, some load is applied, what do you calculate if there is a, say for example, if a point is there at some depth z and it has some or it is away from center line radius r, how do you calculate the shear stress? So, once you know that shear stress, you can plot like this, it is like this only. So, once you plot all the shear stress distributions, like they will be different at different depths, and what we say is that it will have a maximum value. So, pick up that maximum value, then join all these points A dash, A double dash and A triple dash, there are 3 reinforcement layers here. Here also same thing, B, B dash, B double dash and B triple dash. So, you call this as the zone 1, in which the soil is active, in an active condition, in the sense that active the soil is fully participating in this load bearing, and you can say that the other day I was just mentioning about the active resistance and passive resistance, and the other one is a pull out resistance, this is a simple way of remembering. So, this is a way of distribution, that is how it is obtained from elastic stress distribution. Okay. So, you have 2 zones, zone 1 and zone 2, and the classification of the zone 1s and zone 2 is based on this elastic shear stress distribution, tau xz. Okay. And other important thing that we would like to assume is that this is one assumption that we will make, and for n reinforcing layers, the ratio of load per unit area on the foundation supported by reinforced earth to the load on the foundation, the actual old one. Like see, bearing capacity you initially is q naught, now you would like to improve to qr. For example, earlier it was 10 ton per meter square, you would like to make it to 30 ton per meter square. The bearing capacity is at the same settlement. We want to say that normally we say 25 mm is the allowable settlement in the case of footing, some say same number 25, that corresponds to about say 10 ton per meter square. At the same settlement I would like to have, not instead of 10 I would like to have 25. So, 25 by 10 is called bearing capacity ratio. So, this is an assumption that we are making irrespective of the settlement level, we have this loads QR by Q naught as constant, and it's simple assumption. So, these assumptions are required to make the analysis simple. Okay. As I just mentioned, the elastic shear stress distribution is used. This is an expression that we have in theoretical soil mechanics, and if you know the x and z, and b is nothing but the half width of the foundation, right. QR is a load that you are expecting, that is a reinforced soil load, right. Once you have this, and then you can plot this, okay, it is simple. So, what they did was that that point x naught, like I just mentioned in the previous thing, this is a point called x naught, right. X naught is a function of b. So, he is trying to put in terms of the z and x naught is like we have seen that it is related to z. So, to make it simpler, using that elastic stress distribution, one can plot a relationship like this. How is that x naught is varying with different depths? It is simple, straightforward. So, other thing that we assume is, so this plot is useful for us, because what exactly we are trying to do is that you are trying to get this x naught distances. Once you know the x naught distances, this is somewhat very critical in this method, of course. Then we also have the other one, right. We need to get the total length. What is our objective? Objective is to assume some sort of mechanics that they are valid, like elastic stress distribution is valid, and we try to place a reinforcement at these 3 locations. So, the requirement is that I should find out the spacing of the reinforcement, length of the reinforcement, properties of the reinforcement, like if I am using a geogrid, one type, if I am using a steel reinforcement, one thing, anything can be used, any member which can take some tension is sufficient here. So, you try to do that here, and then see that at the point x naught, it behaves like a say for example, there is a kink there. So, the moment the reinforcement, we assume that at that point x naught there is a frictionless roller, and what it means is that there is a load acting here, the moment I assume that there is a roller here, tensile force will act like this, that is what it means. So, that is what the assumption of that at that point x naught, we assume that there is a frictionless roller working, and to make our calculation simple and tell that if there is so much load, there is so much tension here, and then there is also a spacing, and the tension is because of the shear stress distribution, right. The tension is because of the shear stress distribution. So, based on these assumptions, we try to calculate some mechanism methods by which one can calculate the tension force in the reinforcement. So, once you make these assumptions, it is possible to come up with some expressions that I will show you, and also come up with some plots in which some factors A1, A2, A3 and L naught by B are involved, that I will show you how they are useful in the design. And what we say is that you need to find out the tension force in the reinforcement. Actually, we have seen that it is in fact a function of, if I want to say that how much is the tension mobilized, I should have proper spacing and the number. Say for example, this expression gives you the tension force in each member. There is a actually it is a theoretically derived expressions, because it involves essentially elastic stress distribution, and then you will, by using A1, A2 are constants, one can get from these plots, and N is the number of layers, QR is a required bearing capacity, Q naught is original bearing capacity, B is the width of the foundation, and delta H is the spacing of the reinforcement elements. Okay, so the A1, A2 are the factors that I showed you here, A1, A2 I can get from here, right. There is an A1, A2 here. Okay. The A3 factor will also be useful in other pull out resistance. So, once you know this what is the required force and what is the spacing, and if I know A1 and A2, and I can calculate what is the tension. Essentially the concept is that shear stress distribution you are calculating, then you are making some simplified assumptions, and put the put a roller there and then calculate what is that, depending on the load applied, what is the tensile force you can calculate. Okay. Then okay, now you have calculated what is the tensile force you have, that is fine. Say for example, it can be you take a meter length of geotextile or any piece of paper, any material that you take, geotextile, geogrid or something, per meter it has say 10 kilonewtons or 20 kilonewtons or 50 kilonewtons or whatever. Even steel may have higher high tensile force carrying capacity, right. So, you have to have once I calculate that, what is the factor of safety against breaking? As I said, it should not be broken, right. So, what should be the factor of safety? The way that I am calculating here is that I have n is the number of ties per unit length of the foundation. Say for example, you have the B width and you have number say for example, as I said the number of reinforcement elements is important, and how do you calculate that? We try to calculate in terms of the factor of safety. So, we actually specify a factor of safety of 2 or 3 or whatever depending on the code, and you take a simple tie. Tie means a reinforcement like any steel strip. We are using an example of a steel strip here. Width into thickness will be the reinforcement element. N is the number of elements. Fy is the tensile yield strength of the material, tie material. So, if it is steel, you have to take that value. If it is a geogrid, you have to take that value. You want to put timber, take that value. Timber reinforcement also is possible, right. Anything is possible here, and WT, all these numbers are there, and if its numbers are then you know what is say the moment you have placed some materials inside, you know what is the spacing and what is using that expression that I mentioned earlier, one can calculate, and if the factor of safety is satisfactory, it is fine. You can take some width and area cross section of the member, number of members you can calculate, or if say for example, if you are putting a thin some sheet, you say it in terms of the meter length, okay. Then you express that in terms of the meter tensile force also you calculate in terms of the meter length, it is fine. You take some 1 meter strip, 1 meter some thickness, then you will have totally WT, and then you test the same 1 meter strip and you put here, and then it is this thing. So, you will get the spacing, you will get the factor of safety, right. Now, so sometimes what we do is that linear density ratio is another term, like say for example, the other day I was showing you a photo in which you have reinforcements at different places. Say for 1 meter they have some 10 or 15 numbers or something, it can like you take a wire mesh which is available, you put a wire mesh which is it also has some gaps in between, it will not be, it is just a series of tension members, and the term Wn is nothing but the linear density ratio. We use a term which is nothing but the how many number of members are present, that is what is called linear density ratio. Like say for example, if I say 50%, 50% means instead of 1 meter area there is a 50% tension members are present, like if it is fully occupied, we say linear density ratio is 100%, or if you have tension member 1 meter there are only 2 rods, 2 or 3 rods. So, calculate the diameter of each rod. Say for example, in a 1 meter 10 plus 10 20 will be the area occupied by this 1 meter thing, 20 plus 20 divided by 100 will you give the LDR, linear density ratio, okay. Then once you calculate that, that is fine, that is what you get, TFY into LDR, LDR into TFY, it is essentially the same thing, and its next step is it should not get pulled out, it should not simply get pulled out, that is very important. And how do you get that? Again there is a simple expression that you have, you get a term called A3 here, and you have a B and all, it is a gamma actually. L naught is the length of the reinforcement and depth and all that. This is another expression that we have for the pull out resistance. Okay. This is nothing but you have two sides, how do you calculate, as I said, higher is a normal force, higher is a pull out resistance. So, on both sides that is a term, that is why you get 2 here, tan phi mu into normal force. Normal force is nothing but any point is gamma b into height, right. See, z plus df is nothing but the normal force. So, into its gamma gives you that what is called the vertical stress into L naught minus x naught. L naught is the total length, x naught I am subtracting. So, L naught minus x naught will give me this, and this other term, and that comes from the stress distribution, and LDR. Okay. This is all that factor that you get from distribution, and 2 tan phi, okay, phi mu actually. So, now you have a rough idea of how do you calculate this force in the, calculate tensile force in the reinforcement, and how do you check the design. So, I want to illustrate the same thing by an example. So, for example, design a continuous foundation that will carry a load of 480 kilonewton per meter. So, for example, you have a continuous foundation, maybe 4 meters or 5 meters length, and it carries a load of 480 kilonewton per meter using the following parameters. So, the density of the soil is about 16 kilonewton per meter cube, friction angle is known, E and mu of the soil are also known. Okay. Actually, sometimes this information is necessary for you to calculate. Say, for example, in this example, I have given the foundations df equal to 1 meter and allowable bearing capacity is 160 kPa. So, now I am using some reinforcement element, say for example, reinforced ties, some tension, I have decided that some strips, steel strips I am using, and this is a tensile capacity, and friction angle, this is called adhesion angle. As I just mentioned, we use 2/3 of the phi, like it is 30 degrees, let us use 2/3, 20 degrees. Now, the factor of safety against breakages we have given 3, and factors against pull out is 2. These are all some specifications that we should see, and this allowable bearing capacity is also given, design life 50 years is also given. Now, based on this example, we should be able to based on this sort of typical considerations, you can see that 160, like if you take a 1 meter foundation width, it will be 480, right. 160 it is almost 4 times, right. So, bearing capacity improvement ratio is quite high. Why these parameters are required is that sometimes 160 is not given, you can calculate using this, knowing the foundation size, you can calculate the ultimate bearing capacity from shear stress, the shear strength considerations as well as settlement considerations. You take some 25 mm or 50 mm settlement and do that and get that, and then calculate allowable bearing pressure, right. So, the same thing, I assume that to proceed B is 1 meter, and as I just mentioned, I would like to avoid that failure like of shear failure occurring at the top. So, I have just first layer of the reinforcement at delta H is 0.5, and the spacing is also 0.5, to maintain that I have taken 1 meter footing, and then 1 meter I am just placing this reinforcement. Length is still not decided, but at least I know that it should be the foundation size is B equal to 1 meter, and linear density ratio I am just taking it as 65%, okay. And which means that in 1 meter 65% is a presence of time member, like say 0.65 meters in a 1 meter is present or some whatever, right. Then D is also like the other spacing and all that. So, both I am trying to keep DH and D as same, because it is easier to calculate. Width of the reinforcement, I can just take a small strip of 75 mm, small strip 75 mm, very, very small, right. So, number of reinforcement elements, like if I know the width is this much only 75. So, in 1 meter what it means is that if I just say that 0.65 divided by 0.07, I will get 8.67 or 9 elements per meter length, that is what it means of having this much width, okay, you can check. So, we need what we are trying to, so you can always change some of these parameters, it is not an issue, this is an illustrative example, and what we need is that sorry, 450 by 160 is the we need the improvement, it is about 3, factor of safety of the bearing capacity ratio required is 3. So, 16 plus 16, yeah, that it is 3 times, not 4 times as I just mentioned, it is 3 times, we need this number. So, as I just mentioned, we had to calculate the tie force. Okay. So, all these things are known, the expression is known, like I know that Q naught is 16, N is number 4, I assume that I am placing 4 numbers, okay. You can make 3 numbers also, and A1, A2 they are the factors, B A1, A2 I will get from that previous chart, they are standard actually. Once I know that, it is possible for me to calculate what should be the tensile force in the each reinforcement. You can see that all the quantities can be calculated. Say for example, if you want to go back to the previous charts, A1 as a function of Z by B, because I placed at Z by B also you are calculating. So, Z by B 0.5, 1, 1.52 you can calculate, right. L naught is another one that we will see in the other one. So, you will get that, so you calculate all these factors and you will get the tension in the each layer is 18, 20, 21, 26 something like that. So, you have an idea now, like if a geogrid company comes and tells you, sir, what is the material you want, you can say that yeah, I want a bearing capacity improvement of factor of 3 here, and you do have this site of this type of this grade of material, that is one, not this grade, because as I just mentioned we have to correct for damage and other things and time and all that, this, but at least it gives an idea that what should be the number of number required in terms of the tensile force required in the reinforcement as a function of bearing capacity ratio and all other factors. Now, you go to the second term, FB is nothing but the calculation of tie force, tie resistance due to friction, pull out resistance. Here also what we do is that again I try to put the same quantities in a simple, because there are 1, 2, 3, 4 layers, it is easy to calculate like this, and you have this factor A3 in this, right, 2 tan phi mu into LDR, they are all known, A is 3 is known, all that quantities I am just simply calculating here. The x naught is what we calculated in the previous thing, L naught is nothing but the length corresponding to, like that minimum stress level, like it can be again it comes from the previous plot that I just mentioned, one of the previous plots. So, once you know all these parameters, you will get substitute in these numbers and factor of safety you will get. So, what is the factor of safety required? We saw that in the example problem that the factor of safety required against pullout was 2 and bearing tie breaking is 3, right. So, we have to see that we added to this. So, in this case the factor of safety is more than 2 and the top one it is lower, why, because overburden is less, as we just go down the overburden increases and hence the pullout resistance increases. So, you can see the other one which is something like L naught. L naught is something it gives you the length of the reinforcement actually. L naught is nothing but it is 1.55 meters here first level, second level the reinforcement length is 2.6, third one is 3.4 and fourth one is 3.85 meters on one side, okay, one side of the foundation. Okay. Now, on both sides it becomes twice, like for 1 meter foundation you have to go for about 3.85 into 2, it is too big, right. So, you have to really somewhat reduce, anyhow we will see that, but you can increase the footing size, like say B equal to 2 meters or 1.5 meters and try to do some more modifications, that we will see how modifications could be done, but just this this gives a basic idea that you can calculate the tensile force required and also the pull out resistance and other factors. As I just mentioned, now we know what is the factor of safety required. So, one way of calculating, see the thickness requirement. Say for example, I have fixed up the width of the tensile member, it is 65 mm, right. Everything is trial and error here, as long as you are able to economize and then cost effective. Design is something you should be cost effective, it should be satisfying all the design calculations requirements. So, here I use a factor of safety against breaking is 3. So, if I just put that number, I can calculate for, I know the what is the tensile force in each member, right. I calculated for layer 1 what is the tensile force there mobilized, then like that one can calculate, and you can get this thickness required. You can see that the tensile requirement is very, I mean maximum the thickness required is 0.4 mm. Actually, I want to tell you that in this book I have given you all the examples, most of the things that we would be covering from now on. I will have a lot of information compiled in this book. I have this, and I will try to use to some extent this material as well as updated material in this rest of the course. So, thickness, you can see that minimum of all this, the highest is about 0.4 for corresponding to different layers, and I need to also provide for corrosion resistance. What I do is that if the galvanized steel is used, the rate of corrosion is, I know that 0.025 mm per year. Now, I know that it is for 50 years. So, 0.025 into 50 I provide as extra allowance plus 0.4. So, 1.65 mm is sufficient, right. But then normally a minimum thickness of in the market, if you just see, minimum is 6 mm. So, it is fine for us, right. 6 mm is too small. So, you are just using a 6 mm thickness to get a bearing capacity improvement of 3 or even 48 ton per meter square you are giving, it is very good, right. So, hence strips of 75 mm wide and 6 mm thick are chosen for present case. This is a simple example, I mean it is just to illustrate you the principles. And one thing you have seen that the length requirement is somewhat little higher here, previous case, like as I said 2 into L naught will be the length required and it is about 7.7, and for 1 meter footing 7.7, the next neighbor may just shout against me. He will not be happy with what is this, why are you having them reinforced into my house. So, then we need to curtail this. Actually I just mentioned the mechanisms of reinforcement. One is by friction, if the friction is not good, it can be long length, like 2/3 of tan phi is what I have taken. Imagine that you take tan phi equal to tan phi mu, length will come down. Then the other one is bond resistance. So, for example, there are two things like you put some sort of angles which will create bond. The thing is that it should not be able to, you can't pull out easily, there should be some sort of bond resistance developed, like you can see in the case of a pile foundation you have a formula that failure surface develops like this and all that, right. Similar to that we should do that, and we have, see for example as I said, we have geotextiles and geogrids. Why geogrids came? Geogrids came into picture because you have nice bearing members that are present. So, in order to reduce this, the whole objective is to reduce the length of the reinforcement, because you do not want to pay a lot of it could be expensive. So, what we do is that we try to put some sort of bearing members or bearing resistance. This is a simple expression that we will use, where I will just show you that you try to put a reinforcement here and you have a tensile member here, right, like a member here, and this is a normal stress acting, okay, normal stress acting, and this is a bearing stress, and this is actually the bearing stress is acting over with B, and actually this is what I am mentioning, B, all these are foundation with B, and so you can put, depending on the spacing of this, you can appropriately do that. And what I was mentioning earlier, there is a friction only here along the surface. Now, because of this bearing members, it will be like this, the failure surface will be like this, okay, because it is just, we call it a rough footing, to be rough, in the sense that there is no fully it is effective. So, what we do is that we try to take two sides, and S is a spacing and sigma n is a vertical tan phi is B sigma B. This is what we use the terminology called rough, otherwise it is smooth, and we try to get back what is the spacing required, right, based on this. We also have some theoretical expression which is quite useful. A theoretical relationship exists between bond stress ratio and the backfill soil properties obtained from limit equilibrium considerations using bearing capacity theory. Sigma dash B by sigma dash n is a simple expression that we see if you just see the bearing capacity theory. So, you will have this equation which will give you, because the objective is we need to calculate, as I just mentioned in the previous slide, the bearing resistance. This is the bearing resistance, right. How do you calculate? The bearing resistance is a function of normal stress. As I said, normal stress is also applied here. So, bearing stress, how do you get? So, I must get that. So, that is the reason why I have an equation like this, which is a function of the phi of the soil. So, depending on the depth at which I place, say for example, shallow depth, because normal stress is low, you will get some bearing ratio, because I finally have to use this term in this equation, right, to get S. So, you will have this expression, and then once you use this friction angle of the soil like phi equal to 30, and you will get the ultimate bond stress ratio and have some factors there, and you just put some numbers here. What happens is that you will get an idea that the length of the reinforcement is taken as 3 meters, instead of earlier I have taken much bigger, right, 3.87 or something. Now, I will just take B is 1 equal to, and its total length is 3 meters only, like 1.5, right. So, the you should also have seen that x naught numbers, right. X naught is one thing which is something a part of it, x naught plus, see total length is L naught, L naught minus x naught will give you the pull out resistance, and x naught is the length at which directly that location of maximum shear stress, all that. So, with this spacing one can go ahead, and if you want to just calculate how it looks like, you can see that. Is it okay? I want to check. So, I just calculated Z plus df, and then effective normal stress 24 kPa, 32 kPa and all that you can calculate. Bond resistance as per anchor you can calculate, tensile force per meter is already given, we got from the previous table, right, each later, and the factor of safety against a pull out, like I calculate, use that particular equation and then get these numbers to calculate the bearing stress also. And now you see that the factors of safety are more than required, and the fact is that now it is B equal to 3 only, not so when the B is 1.5 meters and you are trying to, it is okay. If you want, you can even reduce, there are different ways of see now you got the bearing resistance as an important contribution. It is a very, in fact the ground anchors that they were using in the olden, and even now we will be taking it up in the other lectures. So, bearing resistance and anchorage resistance is something that is very important in many of the ground improvement projects. So, you can see clearly that this is very useful here. Another important thing is that there are certain guidelines. Okay. The guidelines say that the based on extensive work, in fact even we did about some 10 years back based on some master's thesis, where guidelines for use of geogrids biaxial, like I said, biaxial means it should be the stress distribution should be same in both directions, similar, unlike you have a mono oriented geogrids, right. So, the typical numbers are that first layer of the reinforcement U is nothing but 0.15 B to 0.3 B. So, recommended value is 0.5 B, in fact research shows that 0.3 B is alright, 0.3 B. So, but then they go for 0.5 B. Then spacing of the reinforcement, like what should be the spacing between the two reinforcing elements, again 0.5 B, like some numbers, then Z is another number, B width of this thing, there are all various elements that are involved here, and number of elements he says 5. It is all just that one should one need not go by some of these actual numbers. The fact is that one should be able to cross check and verify, and there are many theories also. This Blinkert theory is just the first theory that was done, but after that there are many theories that came in this line. One should cross check, take a particular example of the same thing and what each theory can give, what is the bearing capacity ratio you are getting, and in fact a lot of plate load test results are also available. Okay. One can check which theory is fitting in a particular situation, and say there are actually some disadvantages are there in Blinkert and Lee method. I would like to highlight to you that say the thing is that you are assuming that it works as a pulley there at that point, right. Like now you have seen that the failure mechanisms, we have seen that we made an assumption, right, that it works as a pulley, but it may not be totally like it work as a pulley there, you are ignoring the presence of soil itself. See what it means is that the moment I say you have a reinforcement like this, it just goes like this and there is a vertical stress acting, there is a tensile force like this, you are ignoring the actual presence of the medium itself there. In the sense there could be a friction and all that. In fact they assumed you are getting some bearing capacity improvement here, but what you actually get in the field may be much more than this because of varieties of reasons. In fact I will show you in the next class that it can be higher also from field studies. So additional information on this would be that we will handle what you have seen in the case of soft soil, the sands, how the bearing capacity could be improved, and the bearing capacity could be improved as I just mentioned because of the actual response of the reinforcement element. We have tensile force developed, we also have frictional, we have because of the tensile forces are developed because of friction and also the bond resistance. That was fine in the case of sands, because sand, even aggregates, like you will take some aggregates that we see in roads pavement, particularly if you see in the pavement design, you are using geogrids and aggregates. You can put a layer of a geogrid on the top of the granular subbase, we call it GSB layer, and bearing capacity will be very good, right. So one can even check how much will be the bearing capacity improvement that one can get, but when you have soft soil, what are you going to do? Soil is so soft that it is not even possible to walk across, or you have to again say the load has to be, you have to say for example many soft soils exist on the coastal areas, and you need to improve the bearing capacity because the bearing capacity is low there. And we have seen various ground improvement techniques like stone columns, we have seen prefabricated vertical drains, chemical grouting, admixtures. There are so many issues that we have seen, but here again reinforcement is also another technique that one should examine, because the thing is that in the ground improvement you should examine all the possibilities, and whichever is cheaper only you can take, whichever is feasible. The thing is, if a particular technique is not going to be useful or it cannot be practically implemented in the field, then there is no point, because and then time, say for example there should be an experienced contractor available, everybody should understand the principles and then start doing it. So if you try to say that there is an innovative technique and I gave that technique, and if they can't use, then there is no use. In this sense we have the geosynthetics have been quite useful, and I must say that particularly when you are trying to talk about soft soils, what we should do is that we can't use in the case of soft soils, if you put a reinforcement, there is no friction, the delta, tan delta will be very low, right. So we do not want to have this type of issue here, and what we do is that you have a soft soil, we put a layer of sand, 1 meter sand or 2 meters of sand, that acts as a loading platform or something, right, whatever you can call it, because whatever is the load that can come, it is just getting absorbed in the sand layer, and the shear stress that can come on the clay layer could be much less than the shear strength of the soil. That is an assumption that we thought one should normally make, but if you are using sand and aggregates, it is fine, but apart from using sand and aggregate, it is actually sands are required, sand and aggregate is required. You can't walk on the soft soil, you have to put some loads of sand and aggregate, then only you can do something, because as I just mentioned, they distribute the loads, right. So, in the same, when you are putting sand and aggregate, why do not you put geotextiles, geogrids and geocells there? That is an obvious question. So, we do that here, and we have a couple of ways of doing it here. And say for example, if you place a first a sand material, and then then put a reinforcement also, there are different mechanisms by which it can improve. As I said, the understanding of mechanisms is very important, because you should know how to calculate. You assume some mechanism, then the mechanism gives you method of calculation, right. So, we can improve the soft soil bearing capacity, and what we do is that we put a some sand layer, and also put some reinforcement in between, and we say that there are 3 effects that will help us. One is a shear layer effect, the second one is a confinement effect due to the interaction between the sand and reinforcement in the sand layer, and additional surcharge effects, right. The 3 things, and we know that the ultimate bearing capacity of the footing resting on the soft soil is Q is Cu NC, NC is 5.14. So, 5.14 Cu is what we know, like say if 10 kPa is that, so it will be 51.4 kPa will be the shear strength ultimate value, and you use a factor of safety of 3, it is much less, right. So, how do you improve this is something that we will see. So, these are all the effects that I am talking about. You have a clay soil here, and it has an underlying shear strength of Cu, right, and if I put some granular bed, we call it granular material, blanket or whatever, and this is the B width of the foundation, right. So, what we do is that if you put the load comes like this, then because of the shear layer effect, there is some sort of resistance. Soil has, the sand has some shear resistance compared to clay, right. So, what you call, there is a shear resistance that gets mobilized here in the both sides. This is a shear resistance because of shear layer effect, right. So, this we try to calculate, that is in fact how much is that, half Kp H square, okay. Ka instead of Ka, half Ka gamma H square is what we do in a conventional calculations. Here it is passive pressure, okay, it is passive pressure here. So, that is why we are trying to use, because it provides resistance here. So, we have to calculate Kp, use Kp here. So, half Kp H square will be the pressure on both sides, okay. So, now that is one important thing. Now, since you placed a reinforcement here, so for example, you are trying to place as a reinforcement here, what is that it is doing? You have already this effect, which is because of this shear layer effect. The second thing is what is called confinement effect. It is providing confinement. Reinforcement acts in this opposite direction, right. As I just mentioned, we just discussed about there is a friction. The moment there is a tendency to come like this, there is a resistance here. So, the resistance is developed on this, right, on the friction. This is a reinforcement member, like up to L naught x naught we have seen, no, x naught x in the. So, you can calculate what is the shear resistance, and if you put a reinforcement like this, it is complete reinforcement, okay. It is a complete reinforcement, and there is a thing that is acting here, okay, that is one thing. So, because of the confinement effects, you are able to get some improvement in bearing capacity. In fact, we say that the delta Q S L is improved bearing capacity due to shear layer effect. This delta, there are 3 deltas coming up here, and the other one, the other most important, other one important thing is additional surcharge effect. Actually, it also has a surcharge effect, because the fact is that it acts as a surcharge. The thing is that you place a reinforcement, it is not just about its confinement effect, it is just that it is also the additional surcharge effect is also there, like there is a load applied on that, and it is valid up to, say for example, if length of the reinforcement is say for PS, it goes up to 0.01 of the shear stress distribution, okay. So, These three things are very important, and if you are able to compute all the three things, then bearing capacity improvement is possible even in the case of soft soil. So, when a granular bed of thickness h of the bulk density gamma s and friction angle phi s is used with reinforcement is provided, so the bearing capacity is increased, the frictional forces developed between the soil and reinforcement induce tensile strains, and tensile strains developed provide confinement effect. In fact, they also provide confinement effect. This will reduce the additional shearing resistance along the vertical plane at the edge. This will induce additional shearing resistance because that is another important component, because what is happening, as I said, at the edges it is creating additional shearing resistance, and which increases exponentially with the distance away from the edge of the footing. So, one is the surcharge effect, the shear layer effect, the next second is the confining effect, third one is the surcharge effect. All three of them, they just contribute and then increase this bearing capacity by these three terms, three things. So, this is called this is possible. So, I would like to just take up a simple problem here, which you can say that so similar case that I discussed in the case of okay, you have a sand in one case, but you also have a clay in some next nearby, but the load is same. How do you do that? The bearing capacity improvement is about we need 480. We have to see whether it can come. So, the underlying shear strength of the soil is 10 kPa. So, essentially what I would like to say is that even we can solve this type of problems using the soil reinforcement technique, and we will take up this in the next class. Thank you.